Okay, good morning. What enthusiasm exists for the topic of interstellar travel was invigorated in 1995 by the discovery of the first planet orbiting a sun-like star, which kicked off the exoplanet revolution. All of us in the interstellar travel community owe a debt to the researchers like Mayer and Quellos who discovered the first exoplanets. They gave us the target for our mission planning. But let's take a moment and look at how the exoplanet researchers view us, the interstellar travel community. When Didier Quellos won the Nobel Prize in Physics in 2019, he gave an interview, and I'm going to play about a 2-minute clip from that interview.
The closest potentially habitable exoplanet is the Proxima Centauri b that was discovered in 2016.
Yes.
And if we decide to send a probe there,
yes,
with our current propulsion systems, it will take some 50,000 years.
Yes.
So what are the most viable candidates for new propulsion systems that are currently under study?
Well, I don't really like this idea of sending a probes. I think it's a sci-fi dream, and I think it's misuse of the money right now. You can study a lot of stuff just by looking. So I think we should be much better to design the kind of equipment we would like to build to try to retrieve as much data we can before sending a probe. I think we are 100 years behind sending any probe at that distance. And even if you want to send a probe with the current technology, I think it's, in 10,000 years, we should reach the technology to go much faster, and we still have this old probe on its way while the time you will move the new one. So I think we should really get a bit more focus. I know there are some people that would dream about that. There's some private sponsors that would like to do that. I personally regret that they're not talking to astronomers about this, because I love the idea to look for life on Proxima. It's a very good program, but not sending a probe. Just build the equipment to just look at it. And we should be able to tell a lot already without going. Now, if you want to go there, the problem you have to face is you better go quick, because otherwise it takes too long. So the speed has to be quite significant. When you start reaching 1% of the speed of light, the mass becomes bigger. So how are you going to slow down that stuff? I mean, if you just have a kind of flyby 1 second to the planet, what's the purpose? So I think we should try to engage better with the people that would like to have this program, and I would really invite the people that are interested by this, and especially from the private sponsor side of you, to talk to astronomers and try to come up with a realistic program. And this idea of sending a probe to Proxima, I think it's just a dream right now, and we should not spend money. You can still dream, that's fine, but spending money to that is just a mistake to me.
Okay, so if a Nobel laureate in physics doesn't understand when relativistic mass increase becomes significant, we have our work cut out for us, okay? So what this talk is going to be about is dialing down the giggle factor that exists around interstellar travel. And I took the title of this talk from a quote I'd always heard attributed to Arthur C. Clarke, that the space elevator will be built 50 years after everyone stops laughing. And for the paper, I researched down where this quote came from, and I was delighted to find out that Arthur C. Clarke actually attributes this to Arthur Kantrowitz, who is my academic grandfather of sorts, for his laser launch concepts. So specifically how this came about was my research group hosted the prior Interstellar Symposium, the 8th in 2023, and as we were building up to that, I was trying to generate interest around it, so I went on something I don't normally do, which is go on a podcast interview that is affiliated with a YouTube channel, which is Universe Today, run by Fraser Cain, and was surprised that this video actually did quite well. So it now has over 700,000 views. And for an academic, this is a whole new world, right? So you're a professor, you publish a paper. If one person reads your paper, it's a success. Okay, so cheat code for any students out there, if you're at a conference like this on a budget, just come up to an academic and say, you know, I really enjoyed reading your paper, and you'll probably get a free lunch out of it. Okay, if you pick one of their less cited papers, you'll get a free dinner out of it as well. okay? So this was really something for me to have people now start emailing me. I had people mailing me books about their concepts for interstellar travel. And so I just said, well, if they listen to me drone on for an hour, at least I deserve to listen to them. And so I started reading the comments on this. Now, I don't believe YouTube comments are usually a fountain of intellectual clarity, but I tried. And every day for about 2 years, over coffee in the morning, I would go and respond to what are now 3,000 comments that have shown up on this video. And one thing I learned is don't post links in YouTube comments. Okay, if you do that, YouTube thinks that you're spamming and you get blocked for a period, okay? And I contacted Fraser about this and he put me on his safe commenter list. But even then, if I would post a link, so as a trained academic, everything I say I want to back up with a reference, okay, a DOI link, but you can't do that on YouTube, okay? So after having my comments disappear, I started writing my comments in a Microsoft Word document and then I would copy paste them in. So if they didn't show up, I could the next day try to post the comment there. So the paper that accompanies this talk is essentially that document. It's about 20,000 words now. And all I did was kind of reorganize it into a FAQ, if you know what that is, a frequently asked questions or frequently encountered comments that you get around interstellar travel. And we have now, as of about 9 a.m. this morning, put this on our research group's webpage. So if you go and get this QR code, you can find this FAQ. There's about 40 comments there. This is a beta release, so I'm looking forward to feedback from people on this. Not everybody's going to agree with probably everything that is said on our website, but at least it's a starting point for us to better communicate. Okay, so the idea today is I want to discuss with you, the interstellar travel community, how we better communicate with the public. So I sort of organized these into kind of 6 categories of comments or questions that we get. Okay, so let's dive into it. The first thing that anybody who's a space enthusiast has encountered is how can we spend money on space when, you know, there's any kind of human suffering or unsatiated human need here on Earth, okay? So the first thing I found useful is to turn the question around and ask the person, well, how much money do you think we're spending? Or how much taxpayers' money are you think being spent on space? And I have found, and there's polls that show this as well, that a lot of people are under the impression that NASA's budget, for example, here in the United States, is 20 or 30% of the federal budget. It is nowhere near that, right? It's about 0.5%. At the peak of Apollo, it was 2 or 3%, okay? So that's the first important fact to get out there is exactly how much money is spent. But it does not get to the moral crux of this question. And this is something which I'm sure everybody in this room is probably engaged in this at some point. What I would say is, find this letter that Ernst Stuhlinger wrote in response to a letter he received from a nun working among starving children in Africa. This was right after the Apollo landing. Now, Stuhlinger is a figure not without some controversy due to his involvement in the German V2 program in World War II. But this letter is really a master class in grace and humility, and I've just never seen it done better. So I would say if you encounter this question, read Stuhlinger's letter, and then we need to think about how to better reformulate this in the interstellar context. Another thing I encounter as an academic, my salary is mostly taxpayers' funding. My research that I spend is mostly taxpayers, Canadian taxpayers in my case, funding. How do I justify spending money on this when the students I'm training are not going to go out and get jobs building starships? Okay? So I grapple with this question a lot, even internally. And my response is sort of two-tiered. First off, what is it that inspires students to go into a difficult field, like in my case, engineering, to get the skills they need to solve the hard problems? So I teach an introductory course for all incoming mechanical engineering students at my university. It's about a class of 200. I've taught it every year for 12 years. And I give an assignment in the class. The students have to pick a picture of something that inspires them to become an engineer. Okay, it can be from fiction, it can be from movies, it can be someone you know, it can be a historical, it can be anything, but send me one picture and then write a page about what that means to you and what it inspires you. And I've done this now for 12 years, so I have thousands of these. I actually do read them, and I maintain a little database of where the topics fall. About a third of them come from space, okay, from astronomy or Apollo or the ongoing new space revolution. Remarkably, in 12 years of doing this, I have never once seen Greta Thunberg, okay, which is remarkable to me because I've seen students that were, younger than her, the same age as her, and now older than her, and never once is that listed as an inspiration, okay? So it's space that is inspiring students to do the hard work in university, to give them the skills to do the heavy lifting we need to solve the problems. Now, the students that have come and worked with me on interstellar travel, what have they ended up doing? I've actually found it's fantastic training, okay? Having to work in a wide open terrain of out-of-context problems, which is what interstellar travel is, has been a fantastic way to get them to work from first principles, how to carve out solvable research problems. And those students that have worked in my group have gone on to find jobs in the deep tech sector and have done very well, okay? None of them are unemployed. Next general category is getting to the stars is impossible, okay? I think the best thing to say is when you encounter this skepticism is we have sent 5 spacecraft to the stars. This is, in my opinion, the most magnificent object our species has ever produced, Voyager 1, Voyager 2. They're going to the stars. Yes, it will take 70,000 years for them to reach it, but don't say it's impossible. We just need to go, what? Faster. We need to go faster. We need to go 10,000 times faster. Where do we get a factor of 10,000? It doesn't come from incremental advances in technology. Okay, it comes from things that scale. Okay, so Joel Jackson is in the audience. He often talks about how antimatter production was scaling something similar to Moore's law for many decades. My colleagues in the fusion community talk about how their progress towards the Lawson criterion was following right along Moore's law. They were basically doubling the density, temperature, confinement time product for their fusion reactors every year or two up until about 1990, okay? So a factor of 10,000 isn't that long if you're writing along a Moore's law like scaling. So what's the banana for? Okay, so I mentioned antimatter. So one thing I have found in talking about the stack of technologies that we're working on for interstellar travel, whenever I mention antimatter, I get some in the audience that say, oh, scientists aren't even sure that exists. Or isn't there an argument about whether there's antimatter or not, or what it is? And I found what people are confusing is antimatter with dark matter and dark energy, okay? And I think we as a community need to do better to absolutely differentiate these, that antimatter is real, it occurs all around us. For some reason, the banana is always associated because bananas are a source of potassium, but upon researching this, I found out that there are legumes and fruits that are much richer in potassium than a banana. It's just the banana is associated with potassium. So yes, it contains potassium-40 that undergoes positive beta decay, generates a positron. Positrons may be not that useful for interstellar travel, but we don't need to get to that level with the public. We just need to convince them that antimatter is all around us. If you've ever had a friend or relative undergo a PET scan, antimatter is used as a diagnostic technology. Okay, so that's a milestone we have to get over. The next thing I've encountered with antimatter is people saying, well, yes, we can make antimatter at CERN, in the Large Hadron Collider. It's 27 kilometers in circumference. How do we ever make, just make a few atoms of antimatter? So that's the next thing I found is, really any particle accelerator that makes new particles is making antimatter. Anytime you're above 10 GeV in energy, and you're making charged particles by conservation of charge, you're making an equal portion positive matter and negative matter, okay? And when high-energy physicists want to make antiprotons to study, they do not use the Large Hadron Collider. It's actually one of these small accelerator rings over here. At CERN, it's the proton synchrotron that is used, which is like 200 meters in diameter. It's this accelerator here, compared to the Large Hadron Collider, okay? And it's small enough that if you optimized it for making an antimatter factory, yes, it would use much more power than the Large Hadron Collider does, but it could probably fit within this convention center that we're meeting in today, okay? So this, yes, I don't know what Joel Jackson's working on these days, but probably best thing would be to work on a time machine to go back in time and prevent this novel and movie from ever being made, right? Because the public now has this perception that if we were to make antimatter in condensed matter form, I've had people say, but if a single atom of normal matter were to touch it, it would be a cataclysmic explosion, okay? No, if a single particle of, a single atom of matter touches antimatter, yes, there's an annihilation, but those are the kind of annihilations that are happening in your banana and in your body all the time, okay? It's really just a matter of slow evaporation of the antimatter. Okay, and then this is the big one, is, well, it's just too dangerous. Okay, antimatter is too dangerous of a technology. Our civilization shouldn't have it. So I used to remember seeing Robert L. Forward talk about antimatter. And when this question came up in the audience, his answer was, we should be so lucky if terrorists or rogue nations or evildoers pursue the antimatter path, because they'll just bankrupt themselves. Because antimatter is expensive. Okay, it's made from E equals mc squared. That means it will always be expensive, whereas nuclear weapons are relatively cheap. In a nuclear weapon, this took me a while to really tease this out. Why wouldn't someone pursue the antimatter route? It's because a nuclear weapon releases much, much more energy than it goes in to make that weapon. Okay, in fact, if you were at Jeff Grayson's class yesterday, he went through the numbers on this, and wow, deuterium looks really good economically, okay? And this was actually explored in the 1960s under the Plowshare program. You could actually take atomic bombs, drop them in a shaft, detonate them, and then harvest that heat to make steam, to make power, and economically it closes, okay? So bombs release much more energy than you put into them. Antimatter never will. So any rational person that is investing any money would never choose to make antimatter as a weapon. What about the laser-driven light sail? So I spent a year on sabbatical with Phil Lubin's group working on his concepts, spent a lot of time talking to Uber drivers about what I was working on, and several times I heard people say, well, 100 gigawatt laser, this would cause environmental damage. You know, what would happen to a bird flying through it? What's going to do to the atmosphere? Well, how is it going to affect global warming? And again, it took me a while to really formulate how to answer this. And I don't know if people know what this is. This is lasers that are set up in the desert of Saudi Arabia. If people wander out in the desert and get lost, the beam that goes up, which is illuminated by dust blowing around, helps them find water depots so they don't starve to death. Okay? What this does is it takes sunlight in a solar panel and converts it into laser power. And that's really all the breakthrough starshot or Philip Lubin's concept would use, would be about a kilowatt per square meter of sunlight that gets reformulated into maybe 500 watts per square meter of laser power and then sent back out again, okay? And yes, it needs to be an enormous scale. It would be tens of kilometers in diameter, okay? But the flux of the laser is really nothing much more than sunlight. You could actually walk through the beam of the breakthrough starshot and look down into the laser and you wouldn't be harmed by it. Okay, it's only when you focus that onto the meter-sized light sail that it becomes a problem. Okay, what was the biggest comment I received of those 3,000 YouTube comments was the dust grain impacts, okay? I got so many comments on this, and I was answering them over and over and over again, that Fraser Cain made a separate video just addressing this comment. So we can see here, Disco Bliss said at just 1% the speed of light, a single grain of sand hitting a spacecraft would be like a nuclear bomb. And it would take more energy to shield against that than you would need for the propulsion. Okay, so lots and lots of comments around this. What if you hit an asteroid? What if you hit an Oort cloud object? Let's tackle the easy ones first. Okay, so the asteroid belt or the Oort cloud is an impenetrable barrier to interstellar travel. Well, I think people are getting this from a certain 1980 motion picture, what an asteroid belt looks like. This is not what an asteroid belt looks like. If you're in the thickest part of our solar system's asteroid belt, what you see is this, which is exactly what you see when you look outside at the night sky. Okay, if you're on an asteroid, you cannot even see another asteroid, unless it's an asteroid moon that's orbiting you. Okay? In the early 1970s, we sent spacecraft through the asteroid belt without even knowing 1,000th of the asteroids that we know about today, and they didn't hit anything. The Oort cloud is even less dense. Okay? Around each Oort cloud object, there is an empty volume of space the size of the orbit of Saturn. Okay? So you could fly through the Oort cloud billions of times blind and you wouldn't hit anything. You will hit dust. Okay, there is dust in the interstellar medium. About 99% of the interstellar medium is dust. You're going to be hitting that dust continuously. Not dust, it's gas. 99% is gas. You'll be hitting that gas continuously. And there's a hydrogen atom about every 5 cubic centimeters. But we know what happens when protons hit us when we're moving at these speeds because of something called sputtering. So if you've ever taken an electron microscope picture, you've probably sputter-coated your sample. What sputter coating is you use a little particle accelerator to knock atoms off. And we have studied this up to MeV level energies, which is the energy level of these protons coming at us. So we know what's going to happen. It's going to cause a slow erosion. And by the time we get to Alpha Centauri at 20% the speed of light, it's on the order of microns is the amount of material that's going to be eroded away. So gas is not a problem. Dust is a problem, okay? And there was a YouTube commenter that said, why aren't engineers thinking about this? Well, we are. In fact, I think when I joined the interstellar community actively about 10 years ago, I was kind of known as the dust guy because I was always talking about this. You know, we need to study this problem because we really can't simulate those dust grain impacts in the lab. So how much dust is there? And this is something that I spent a lot of time trying to wrap my head around until I heard a nice anecdote about American astronomer Harlow Shapley, who used to come into a classroom and say, if I took all the dust between us and the center of the galaxy and collected it together and started rubbing it on a chalkboard, how many sticks of chalk would I go through to represent all that dust? You know, how long would it take me to do that? And the answer is, you know, we sort of challenge the students, tell me when to stop. And the answer is stop right away. It's basically 1 or 2 rubs of chalk on a chalkboard is the total amount of dust between us and the center of the galaxy. Okay? It's micrograms per square meter. In a microgram of dust, however, there are trillions and trillions of little, you know, nanometric and submicrometric dust grains. So they are going to hit, okay? And they're going to hit a lot. Every second, you're going to see little flashes going off, but they are not atomic bombs. They're about 1 joule of energy. And 1 joule of energy is like a camera flash or a starter pistol or a firecracker, okay? So the larger dust grains is an unknown question, and that is something that all these commenters have forced me to go back and rethink a little more carefully, and we can talk about that maybe later. Jeff talked a bit about this yesterday. It's something we need to know about, and it's why we need to send an interstellar precursor mission out into the ISM. I think I'll skip this. One thing that didn't show up in my FAQ, and one thing I feel a little deficient in my thinking on interstellar travel is I actually don't spend a lot of time thinking about humans versus robots. We'll probably talk a lot about this week as we do at all the interstellar symposia. I mean, my thinking is always sort of what's in Carl Sagan's quote here, you know, when we actually do launch the interstellar mission, I think the boundary between what's us and what's the robots will get to be pretty blurry. Okay, so here's the link for the FAQ again. I'll just give a final couple words of advice or my suggestions in communicating with the public. One thing is, yes, interstellar travel is hard. This is the most difficult thing we can contemplate doing. Don't skirt how difficult this is going to be. Next, you know, get excited, get enthusiastic about this topic when you talk to people, but we're not at the stage yet we're recruiting people to join the crew of an interstellar mission, okay? Don't feel like you have to force them to sign on to this. We're just trying to dial down the giggle factor by conveying, you know, a few of the concepts that I talked about today and more you can find on my FAQ, okay? Be patient, okay? I once read that it takes 15 times of repeating something for people to remember it, and I thought that didn't sound right. Then I became a university professor, and I found, okay, maybe that's right. Then I became a parent, and you find out that's probably conservative, okay? It takes many, 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 many repetitions of a concept to get it across. And if people aren't getting it, that's on you, okay? If the person you're talking to didn't understand it at the end of your conversation, came away still not getting it, that is your fault. It is your responsibility to listen to your conversant and make sure you pitch it at their level and listen to them. They probably have something you don't know that might surprise you, even relevant to the topic. And finally, keep it real. What I mean by that is, I don't know if you noticed, but in my talk today, I only showed pictures of real things. And I think in the age of AI slop, we might be suffering from a little bit of overload of concept art. I love it. I generate it now that we have all these wonderful tools. I make cool renders of interstellar spacecraft as well. But I'm finding in my public talks that it's really important to show pictures of hardware and bananas and, you know, real particle accelerator hardware to keep it real. I don't want to drift this off into something that's too abstract. So that's it. Again, just start of a conversation, and I look forward to people's feedback on our FAQ. Anyone want to volunteer the most frequent question they've had when they discussed interstellar travel with friends and relatives?
Yeah, certainly the angels and demons and does antimatter explode? I mean, even NASA and NIAC, that I had to address that because it became such a big issue.
Yeah, we got to work harder on that one, yeah.
I find that the best answer when somebody says, we're wasting too much money in space, is to look at them and say, what do you think we're doing? Flying up a couple 100 miles, opening the hatch and throwing out gold bars. And when you hit them that way, it has a tendency to make them stop and think. Because now then you get to say, well, what are we doing with all of that? I mean, we just heard about how the investments in bio could pay off in biotech and in medicine. And all of these different things, it's one of those great arguing points, yes.